Hi everyone, thanks for joining this talk today. I am Huriye Khalaizadeh from Deakin University in Melbourne, Australia. In this talk, I'm going to present the research done by a group of Bachelor of Software Engineering honors students I supervise at Monash University. The research is done and the slides are prepared by Lachlan, Brianna, Alice, and KG. This research explores a solution to the issue of visual accessibility for software development. In particular, the idea of making low-code development more accessible for those who rely on the use of screen readers. Visual impairments vary in severity and have different impacts on the person's ability to learn, work, and interact in their environment. Those with visual impairments generally rely on the use of assistive technologies like magnifiers, keyboard shortcuts, and screen readers to navigate computers. Our research focuses mainly on keyboard shortcuts and screen readers. Making web content and software development platforms accessible ensures that those with disabilities are not left behind and can make the most of new technologies. There is a set of web content accessibility guidelines that outline the key inclusions for accessibility. The content must be perceivable, operable, understandable, and robust. Many tools have been created to improve software development accessibility. However, almost all of these research focuses on code-based development environments rather than low-code alternatives. Low-code is an approach to development that is designed to be used by those with less technical knowledge, as it abstracts away a majority of the specifics that would come with building software, like syntax and platform requirements. These days, this is the way many are introduced to software development, as it's more technically accessible and requires less background knowledge. In order to bridge the gap that a lack of accessibility creates, we need to have more diversity in the development teams who build the software. The current problem is that visually impaired people are left out of the conversation mainly, and accessibility is usually an afterthought because those making software often don't have accessibility requirements themselves. In this piece of work, we wanted to know whether we can extend a low-code IDE to better meet the accessibility needs of people requiring screen readers. Firstly, we were looking at IDE selection. We wanted to know how accessible are the existing low-code IDEs for people who rely on a screen reader. And we wanted to build an extension to bridge the usability gap we found when answering this question. So the second research question was, can we build an extension to make low-code IDs more accessible when using a screen reader? And finally, we wanted to find out whether the extension make the low-code usage experience more accessible for screen reader users. So we decided to extend a low-code IDE to fill the gap in existing research. We also wanted to work on an open source project that will remain maintained after this research has completed. And finally, we wanted a tool that can be improved with the current accessibility guidelines. Although there were many low-code tools available, our final choice for this piece of work was Node-RED, as it best met all of our selection criteria. It is a low-code approach. It is the most popular open source project among our selections, and it has yet to implement many accessibility related features, which can be improved with current accessibility guidelines. We present an extension of Node-RED called Node-Read with extra keyboard shortcuts that didn't intercept with screen readers. Our extension is designed to make development more accessible to people with screen readers. We wanted to show that if done properly, Node-RED didn't need additional features to become visually accessible, and simply well-structured documentation and well-implemented features were sufficient. In particular, we found that keyboard shortcuts, which are essential for screen readers and screen reader users, were being intercepted by the screen reader itself and didn't work as a result. What we ended up doing was that we remapped these features onto different keys and tested the changes on a variety of different screen readers. We ran study sessions with 12 participants. Half of them used our version, Node-RED first, while the other half used Node-RED first. Each group then swapped, so every participant eventually used both versions of the software. We used a thick, slightly transparent overlay to simulate the functional effects of low vision. As you can see, it makes it nearly impossible to read most text, but provides some visual input. Participants took control of a researcher's computer using Zoom and interacted with the software using the NVDA screen reader, which is what creates the blue and red rectangles on the screen. As for the study itself, we walked participants through 6 tasks, and at the end of each run-through asked them to fill out a questionnaire about their experience. This meant that each participant filled out the questionnaire twice, once with their impression of our extension and once with their impression of the base version. We analyzed the recordings for useful information. We summarized the questionnaires by their results and analyzed for trends. We identified the limitations of the study and finally provided recommendations for future studies. Here's the overall feedback we got on the application for both Node-RED and Node-RED. As you can see, results vary and don't definitively report a better experience in either version. Overall, there are notable improvements on how participants responded to the keyboard shortcuts in Node-RED over Node-RED. This would indicate that the implementation of useful keyboard shortcuts and their inclusion in tutorials is valuable to end users. On the tutorial feedback, results vary, but some clear results are that users preferred adding nodes in Node-RED over Node-RED, and users said they couldn't as easily complete the tasks on their own for Node-RED over Node-RED, which might be because they needed to memorize shortcuts. We had some notable limitations in this research that I aim to overcome in my future research. First off, we simulated visual impairments using an opaque filter, as we only had one visually impaired participant among all our 12. This means that the results of this study may not necessarily cause the same result for a group of visually impaired participants. We limited the scope of our research to existing but inaccessible features, as previous studies identified that many visually impaired developers are simply unaware of existing accessibility features. Therefore, we cannot be certain that new features would provide additional benefit. Finally, we noticed that participants responded differently to tasks that had not been changed between the software versions. While it's likely that this is due to a small sample size, it does call into question the accuracy of comparisons between each participant's to questionnaire responses. For our future research, a key avenue for further research is audio-based action discoverability. Providing users with an audio overview or suggestions of the potential next steps that they can take can increase action discoverability. and require less shortcut memorization for users, which in turn makes the process of learning to use the software less daunting. Many participants reported difficulty wiring nodes together, which can't be completed with a keyboard shortcut in either software version. Further research into the accessibility of Node-RED could include the creation of additional features which provide alternatives to difficult tasks such as this one. Thank you so much for listening to my talk, and I'm happy to take questions.